Good morning everyone. So we're going to do one final lesson on sketching trig waves, and I hope that this is going to help people. It's obviously something you can do more than once if you want to as well. Now, we didn't have a chance to take your books home yesterday, so you won't have any squares to draw on, or you probably won't. If you do, then you might find it easier, but I thought I'd do all of this just on plain paper, and you can do the same if you like. It's one of those topics where you've got to think about whether or not you think of maths, as an art or a science. A lot of people think of it more as a science, but I often think it's more like an art. And trigonometry is one area where the two sort of go together. So I'd like you to copy this down and just have a little go at sketching what the sine wave, the cosine wave, and the tan wave look like. In a moment, I'll put mine on. Don't worry if you get it wrong a little bit. You can always just sketch it again from what I've done. That's part of the process of getting these things firmly locked in your brain. Okay, so the sine wave starts at 0, and then it just goes up, and it goes down, and it goes back again, being basically symmetrical. Now that I've done that, I'm going to put my x-axis in there, and I know that it's a full turn, 360 degrees, that gets me to there. Half a turn is 180 degrees, gets me to there, and it's starting from 0 there. I also know that it goes up to 1, and it goes down to -1. I'll draw the other two, and then I'm going to come back to that, and we're going to look at something called the unit circle a bit. Right, so the cosine one, it starts, it's basically the same wave as this, but it starts at that point there. So when I say start, I mean starts here, and then it's going to go. And I always find it harder to draw a nice cosine wave than a sine wave, just because of where it's starting from. So that's going to be my 360 degrees. My 180 is going to be at the bottom of the trough. The peak of the wave is 0 and 360, and that's going to be +1, and we've got -1 down there. Finally, the tan wave's the one that can go off to infinity. So I'm going to just draw it doing that first of all. Starts at 0, and then I'm going to pop my asymptote in there, and that's at 90 degrees. I'm going to do the same thing there and then continue it up. That's my 180. And you get two periods of the tan wave in 360 degrees. So there's our x there. And I'm not going to, and I don't bother putting anything on the y-axis because it's going up to infinity and beyond, and down to infinity and beyond. That's why we have the asymptote, because at 90 degrees it is both positive and negative infinity, and that can't be. Now we're going to look at the unit circle. Now you may say that's not a very good circle, and you're right, but apparently being able to draw a perfect circle without a compass is a sign of a psychopath, so that's my excuse. You're safe with me. Right, so there's our hypotenuse of 1, and on the unit circle we would be looking at this. Well, that looks like a 45-degree one there, doesn't it? It's a pretty much central. So I'm going to start that again, actually. So here we go. Let's see if I can do a slightly better circle. Maybe if I put in some points about the same distance around the outside and go there. That'll help me. That'll help me just to get something that looks a bit more circular going on. Right, that's a bit better. So now I'm going to think about a 30-degree angle, so that's going to be more like something like this. And you may remember that 30 degrees is one of those ones that we're meant to remember the trig ratio for. And the opposite, if it's 30 degrees, because sine 30 is a half. So when it's halfway up there, that would come in at 30 degrees. Now, what that means is if this is 1 unit long, or 1 centimetre or whatever, the opposite length there would be a half. The adjacent is going to be a bit trickier, but we won't worry about exactly what that is right now. We're just going to think about the sine curve. So, because the cosine curve sort of is derived from it anyway. So, if I had 30 degrees there and that length being a half, if you imagine this hypotenuse as being a stick that can rotate around the point at the centre. If I was to rotate that stick round this circle until I got to a point opposite it here, so that this was 30 degrees, I would also have a height of a half. And this is my y-axis here, and that's positive 1. So I'm getting to positive 0.5 when that height is a half. Now, if you consider the angle as starting from the x-axis and going round the opposite way that we would do for bearings, going round anti-clockwise, we've got a 30-degree angle there. And then from there round to there would be 90. And then it's another 60 degrees to get to there. So this would be 90 plus 60, 150. Now if we go across here and read down here, that would give us 150. And if you put sine 150 into your calculator, you'll also get an answer of 0.5. Check it if you like. So there we've got sin 30 equals a half. If I just go back there and change that to 150, it still equals a half. Now, if I continue on my journey round to the point that is exactly at negative a half, that angle there with the x-axis will be 30 again. But if I were to consider it going all the way back from here, that would be 180 plus 30 makes 210. And 210 would be just there at negative 0.5. And then if I were to continue that on until my stick got round to here, and that angle there was 30 degrees, the whole way round from there is going to be 360 minus 30, isn't it? It's going to be 330, which is how far back from 360 we are there, the same distance as that there, so that would be 330 degrees. So that's what we're starting to build up. Now, we could, if we wanted to, draw that curve again. By the time it gets to 720, it'd be in the same place, because I could keep drawing that stick, and I could keep going round and round and round, and the positions would be the same. That's what's going on with the sine wave. And it's also the same idea with the cosine wave, and that's what this is representing when we draw it all the way along here, is what's happening when that little stick is going round and round. Next up, I'd like to think about y equals sine x. Now, I know some of you got the idea of this, but I know a lot of you won't. And even those of you that did, it takes a while to get really solid in your brain, so it's worth going through again. So to do y equals sine 3x, we're also going to think about y equals sine x. And we're going to think about the values for now. So I'd like you to draw out a table looking like that for y equals sine x, and another one that looks the same for y equals sine 3x. Something like that. I haven't done a brilliant job in terms of presentation there, don't worry. So take your time, use your calculator, fill out the values, pause the video now because I'm about to show you what they should be. So what's happened here? We've got all our usual values that we've done before in class for sine x, but sine 3x has given us half our values are 0 and the other half are either 1s or negative 1s. Well, what we're doing is, before we do apply sine to the number, we are timesing our number by 3. So we've got our 0 times 3 is still 0. We've got if you times 30 by 3, you get 90. So that's that value. If you times 60 by 3, you get 180. If you times 90 by 3, you get 270. And finally we get 120 for 360. So these are the values here. are for what's happening as sine x goes further along the curve, and we're getting, by the time we get to 180, we've got 3 180s. By the time we get to 360, we've got 3 360s, which is 1080. It's going to create 3 whole cycles in a shorter time. So when it comes to sketching, we could sketch our normal y equals sine x, and we say, yeah, I know that's going to do that. But when it comes to y equals sine 3x, if I do that in red, that's going to happen 3 times by the time we get there. So how do we sketch that? Well, I know it's going to hit it at 60, and it's going to hit 0 again at 120. So I need to divide this into thirds. So if I do that, then I'm still going up to 1 and down to -1. That's still my 360 degrees there. But now I'm going to be passing through the x-axis every time I've got a dot there. And that includes here as well, doesn't it? So that is 1.5 cycles. And then, oh, there we go. There we go. And we have got 1, 2, 3 full cycles of the sine wave happening. So that's my y equals sine 3x. And the other one is y equals sine x. So if we multiply our value of x by 3, it's going to create kind of like a squashing effect. It's called a stretch by a scale factor of 1/3 because it's happening 3 times within what it should do. It doesn't sound right to call it a stretch. It'd be nice to call it a squash, but that's not so technical. Okay, so that's that one. Now we're going to have a little go at doing y equals 2 sine 3x. So I'd like you to draw the same table of values and then have a little go at sketching it and then see if you agree with me. Now I'm not actually going to bother using my calculator because I'm just going to think about what this means. Sine 3x would get us all of these values. Timesing that by 2 is what this is saying, isn't it? So we work this out, then we times it by 2. It's kind of thinking of sine 3x as being something like that you would do like indices before multiplication. So then if I times all these values by 2, all the zeros are still going to be 0, because if you times 0 by 2, by anything, it's still 0. And then the other values are going to double. So my 1s are going to double to 2, and my -1s are going to double to -2. And once I've done that, it starts to be a little easier to think about what's going to happen to my curve. In fact, shall I draw it on there? No, I don't think I will. I'm going to sketch it here again. So I know I'm going to need 1, 2, 3, 4, 5, 6. Yes, I need 1, 2, 3, 4, 5, 6 gets me to 360. And this time I want to go all the way up to 2. And down to there. So now I'm going to have to go, oh, I've pushed that in a bit more, so I've got to go back to 0 each time I put a dot there, and I'm just sketching it through like that, and that is y equals 2 sine 3x, just the same as this one, but this has got a vertical stretch of a scale factor of 2. So it's a little bit strange. When it's inside the sine, multiplying shrinks it or makes it happen more often, so or increasing the frequency, as they would say in physics. And then when you multiply it outside of the sine, so actually afterwards, but it's written before, a little bit confusing, that's going to make the effect bigger in the y-axis. Right, so we've got to that, and now we're going to look at the most complicated one of them. I'm just going to build this up to y equals 2 sine 3x plus 5. So if you think about it, we've already worked that out. Make another table of values, but then make sure you do the plus 5. Should give you something like, just adding 5 to all of these values, 5, 7, 5, ooh, 3. No, is that 3? Yes it is. 5, 7, and so on. And so when it comes to sketching it, I would be tempted to do this sketch first of all, and then just say, that's not where I want my axis. I want my axis to be down below. I need to change these values, don't I? So that is not a 2, that becomes a 7. This is not a negative 2, that's become a 3. And the 5 is where the x-axis used to be. So all I would have to do would be to continue that down. So that's down to, right, so if 0 is about down there, I would have my x-axis down there. Right, now all I want you to do now is have a go at sketching y equals 3 cos 2x minus 1. And it's up to you how you do it, but if you're up for the challenge, what I'd like you to do is just start by sketching y equals cos x, and then sketch y equals cos 2x by thinking about what's happened, then sketch y equals 3 cos 2x, and then apply the negative 1 at the end. And having done that, then do your table of values and see if it agrees with what you've done. So pause the video, because I'm about to start going through it like that. I'm going to put the table of values in at the end. So I'm starting with y equals cos x, and I know that that's going to be doing that. There's me 360, there's my 180. Then I'm going to say, right, cos 2x, what that's going to do is that's going to make me have twice the number of waves, because I'm going to be getting the value of 360 when it's only 180 as my x. So where have I got? So I've got a 0 there. So if I go halfway along there, that was 90 degrees, that'll be 45. If I go halfway from 270, what's half of 270? 135, that's going to be halfway between there and there. Then we get up to 180 is there, and then we're going to do the same thing again. So that's at 270, but it's going to happen at 145, so it's going to be halfway between there and there, and then it's going to be halfway between there and there again. So, starting from the same place, y equals cos 2x would do wherever I'm putting my dots, I'm going back through 0. So it's going to look like that. Great. Now the next one to think about is, so that's y equals cos 2x. I'm going to need another colour. So if I multiply by 3, so I got 1 there and there, I had a negative 1 there. I'm going to have to go up, aren't I? So that's going to be a bit messy. So I'm going to have my 3 up there, and I'm going to be going down that far, down to negative 3 there. But I'm going to do the same thing. I'm just going to concentrate on those bits going through the 0 and through the 0. And I know this is a little bit messy, but hey, sometimes you have to get a bit messy. Y equals 3 cos 2x. And then the last thing we've got to do is take 1. And if I'm going to take 1, well, last time I was lazy, wasn't I? I just changed the axes. But if I'm going to do this all on the same thing, I'm going to come down 1 to 2 there, and I'm going to go down 1 to negative 4 there. And I'm going to draw the same thing, basically, but it's going to be bottoming out there. And also, the axis is going to come down 1, so the middle of my wave is going to be happening along there. So I need to think about that. That's where my wave is going to be centering. So I'm going to put some dots on there so that I sketch that through in the right place. And otherwise, it's the same as the one that we've done. Now you may be thinking, yeah, that's a bit messy, sir. So maybe we should sketch it out again now that we know what it looks like. And when I do this, I'm thinking about this bottom of my page here, so I've got to get this right. I'm going to go down to -4. I know that exactly halfway in between is going to be -1. My axis, therefore, if I split that into 3, will be just about there. And then I've got to have I've got 1, 2, 3, 4 of those things happening, haven't I? How am I going to do that? Let's just space it out as the 360 I know is going there. So I'll get half of that to 180. And then think about where those points were relative to that. I'm going to dot in that because there's nothing wrong with doing that. So we've got 2 points where it's going through 0 like that, and then either side of the 180 and the 360. And I think these ones got a little bit not quite separated enough, so I think it's more like that. And then we're going to go straight down to the bottom, straight up, straight down, and it doesn't have to be perfect, so it's going to look something like that. Right, well I hope that's made things a little clearer for you. If it hasn't, watch it again. Anyway, have a lovely half term, and if you do get on with that, I could even give you a little challenge. If anyone wanted to upload a little challenge to me, voluntary thing to do here, you could have a little look at what you think y equals, what should we go for? We could go for 4, that'll be big, won't it? 4 sine x, sine, what did we have before? Let's go 4 sine 5x. Oh, that'd be nasty. And let's add 2 to it. Okay, so have a little go at that if you want to, see how that pans out. And we'll have a look at that curve on the first day back. And if I forget, don't let me. Okay, cheerio folks, have a great half term. Bye.